Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 35. In this lecture, we'll discuss pressure and gravity. This topic is covered in Chapter 14 of our textbook by Surway and Jowett. In this lecture, I want to discuss the effect of gravity on pressure. However, before doing so, let's review what we learned in our last lecture on pressure. Last time, we learned that all fluids exhibit pressure. When I say fluids, I mean gases and liquids, so solids are exempt from this discussion. But any gas and any liquid naturally has some pressure. That pressure is essentially the result of collisions between the molecules or atoms of the fluid and the walls of the container. So in gases and liquids, the molecules or the atoms are relatively free, and therefore they can move around with relatively high velocities. They can collide with the walls of the container and exert a force on those walls. If we take that force and divide it by the area of the walls of the container, what we get is the pressure of the fluid. According to this picture, if there are more particles inside the container, then the pressure should be higher. And if the temperature is higher, then again, the pressure should be higher as well, because a higher temperature means more rapidly moving molecules, and molecules that move faster exert a greater force when they are involved in a collision. So we'll make all of this much more precise a little bit later, but for now we want to examine the effect of gravity on this picture. So far we have not really talked about gravity. We're assuming that these molecules are unaffected by the force of gravity. That would be the case if this container of gas is somewhere in outer space. For example, if you live in the International Space Station in a microgravity environment, then the air inside the International Space Station would be essentially unaffected by the force of gravity. However, if you live here on Earth, then gravity plays a significant role. It turns out gravity can actually modify the pressure inside the container. It turns out gravity essentially enhances or increases the effects of pressure. So you don't need gravity to have pressure, but in the presence of gravity, pressure is usually increased. To better understand that, consider an open cylinder here on Earth filled with water. So to have a concrete example in mind, we're imagining a cylindrical container filled with water, but the shape of the container isn't very important, and you can imagine filling the container with any liquid or gas that you like. The important point is that molecules at the bottom of the container must support the weight of all the molecules above them. Now, this is essentially true of all the molecules in the container, but a water molecule near the surface has to support or bear the weight of less water above it, while a molecule at the bottom of the container has to essentially support the weight of all the water above it inside the container. This is important because pressure is force divided by area. And the force we're talking about here is the force of gravity or the weight of the fluid. If the weight or the force increases with increasing depth, then the pressure should also increase as we go deeper inside the fluid. To make that more precise, let's consider a specific depth d. So consider a molecule, for example, swimming around inside the container at some depth d. What's the weight of all of the water that is above that molecule? Well, we know that weight is equal to mass times gravitational acceleration. We also know that mass is equal to volume times density. So we often define density rho as mass divided by volume. Rearranging that formula, we find that mass is equal to the volume of the water above that molecule times the density of whatever fluid we're considering. Now the volume is going to be equal to the cross-sectional area times the depth that we're interested in. If the container is a cylinder with a circular cross-section, then A is essentially the area of this circle here, But if the container is square in cross-section, then this A here would be simply the area of a square. This expression is important because it tells us the weight that a molecule at some depth d must support above it. Pressure, of course, is force divided by area, so by taking this expression and dividing by area, we find the pressure at depth d. Of course, if the container is open at the top, we should also consider the pressure of the ambient air or the atmosphere that might be present. So finally, we can say that the absolute pressure at some depth d is equal to whatever the surface pressure is plus the depth that we're interested in times the density of the fluid times gravitational acceleration. If you're conducting this experiment here on Earth, then G is going to be 9.8 and P sub 0 is usually taken to be 1 atmosphere. On the other hand, if you're conducting this experiment on the moon, then G would be approximately 1.6, and because the moon does not have an atmosphere, the surface pressure could be taken to be 0. The important point here is that pressure increases with depth and it does so linearly. I used water as an example to discuss the dependence of pressure on depth, but of course this equation is true for any fluid, including air. Evangelista Torricelli was the Italian scientist that invented the barometer, a device for measuring pressure. In 1644, in a letter to a friend, he stated, "We live submerged at the bottom of an ocean of air." This fact is sometimes easy to forget, but you have to remember that we basically live at the bottom of an ocean that is approximately 100 kilometers deep and consists of air. What that means is that we can apply this formula to the atmospheric pressure here on Earth so long as we know the density of air. At the very top of the atmosphere, where we're exposed to the vacuum of outer space, the pressure is 0, and as we go deeper into this ocean of air, the pressure increases. Right here on the surface of the planet, the pressure is 1 atm, or 101,325 pascals, but at higher elevations, the pressure is less. At the top of Mount Everest, for example, the pressure is approximately 0.3 atmospheres. This is part of the reason why it's difficult to breathe at the top of Mount Everest, because your lungs have to essentially work harder to pull air in. The outside pressure is not helping to push air into your lungs. The important point here is that this formula is valid for an ocean of water or an ocean of air or any fluid that you wish to consider. So let's do a practice problem to get some practice with our pressure formula. Suppose you're swimming at the bottom of a swimming pool with a depth of 3 meters in Malibu. What is the water pressure at the bottom of the pool? You're also given the density of water and the fact that 1 atm is equal to 101,325 pascals. Now, the swimming pool is in Malibu, California, which means it's by the ocean, which means it is at sea level. So the important fact here is that 1 atm is defined to be atmospheric pressure at sea level. So what we can say is that just outside of the swimming pool, the ambient pressure due to the atmosphere is exactly 1 atm or 101,325 pascals. But of course, as one goes deeper into the swimming pool, the pressure increases due to the weight of all the water above head. And to calculate the pressure at the very bottom of the swimming pool, we use this formula here. You should be using SI units, of course, so P sub 0 is going to be 101,325 pascals. That's supposed to be the pressure at the surface of the swimming pool. The depth, of course, is 3 meters. That's the depth of the swimming pool. Rho is the density of water. We're assuming that the swimming pool is filled with water, like most swimming pools. So that's going to be 1,000 kilograms per cubic meter. And since this swimming pool is here on planet Earth, G is going to be 9.8 meters per second squared. Plugging in all those numbers, you find that the pressure at the bottom of the swimming pool is 130,725 pascals. Our pressure formula implies a couple of important facts about the nature of pressure. The first important fact is that the pressure in a static fluid at a given depth is uniform, meaning that the pressure is the same everywhere at a given depth. Here we are talking about static fluids, so fluids that are at rest. We'll discuss dynamic fluids, fluids that move, fluids that flow through a pipe, for example, in a later lecture. For now, imagine you have a container of arbitrary shape and imagine that it is filled with a fluid at rest. The pressure at a given depth is the same regardless of where you are at that depth. So whether you're in the middle of the container or closer to the walls, so long as the depth is the same, the pressure is the same. The second important fact is that the pressure in a static fluid at a given depth is isotropic, meaning that it is the same in every direction. Remember that we're talking about fluids here, and molecules in a fluid are free to move in every direction. So molecules at this point here inside the fluid are certainly moving down, but they could also be moving to the left or to the right, upwards or diagonally. What that means is that in that region, there is pressure acting in every direction, and it's the same pressure. You can calculate that pressure using the pressure formula. Once you have it, you can say that the molecules at that point are exerting the same force in every direction. To better understand the uniform and isotropic nature of pressure, let's do a practice problem. What we have here is a funny shaped container filled with some fluid. If you like, you can imagine you have a flower vase and that you have filled the vase with water to the brim. Here what we want to do is simply compare the pressure at 6 different points inside the fluid. We're going to use our pressure formula to compare the pressure at various points. Recall that according to our pressure formula, the pressure is equal to the surface pressure, so whatever the ambient or atmospheric pressure is at the surface, plus depth times the density of the fluid times gravitational acceleration. Let's begin by comparing the pressure at points A and B. We can say that the depth at point A is 0, so the pressure at point A is simply equal to the surface pressure, usually taken to be 1 atm. B, of course, is at a greater depth, so its pressure must be greater than the pressure at point A. Molecules at point B have to support the weight of all the water above them. A molecule at point A does not have that burden. So it should be pretty clear that the pressure at B is greater than the pressure at A. What about points B and C? Well, once again, we can see that point C is at a greater depth than point B. Depth here is measured as a positive number relative to the surface of the fluid. Since the depth at point C is greater, the pressure at point C must also be greater. What about points C and D? As you can see, points C and D are at the same depth inside the fluid. Another way of stating the same thing is to say that the y-coordinate of points C and D is the same. You can set up your coordinate system with its origin at the bottom of the container or at the top of the fluid. In either case, points C and D would have the same y-coordinate, therefore they would have the same depth, and therefore they would have the same pressure. This point is a little bit confusing for some students, in part because you might think that at point C we have to support the weight of a much larger column of water compared to point D. Now that would be true if we were talking about solids. For example, if we were talking about a structure made of solid bricks, in which the bricks are stacked on top of each other, then certainly a brick over here would have to support more weight than a brick over here. So for example, if we're worried about the bricks getting crushed, for example, by the weight overhead, a brick over here is more likely to get crushed by the weight of all the bricks above it compared to a brick that is located over here. But of course, we're not talking about solids, we're talking about fluids. In fluids, the molecules are free to move. They're essentially randomly located, and they are moving essentially in every direction. What that means is that a molecule that is located here 1 second could very easily end up over here the next second. And it can carry its energy with it, and when it collides with a molecule there, it will transfer some of that energy. That collision could result in a force that points in the x direction or in the y direction, or really in any direction, depending on the velocities of these molecules. So we sometimes describe this very complicated situation by saying that the force is being transmitted in every direction. So long as we're talking about 2 points at the same depth, we can assume that molecules at that depth have the same energy and therefore exert the same force and consequently must have the same pressure. Therefore, pressure at C must be equal to the pressure at point D. What about points C and E? Well, E clearly is at a greater depth, so we can say the pressure there is greater. Comparing points E and F, we can see that again, they are at the same depth, so they must have the same pressure. And comparing points F and C, we can see that F is at a greater depth compared to the very top of the fluid than point C, and therefore the pressure at point F must be greater. Let's do one more practice problem, very similar to the last one we did, but this time we're going to compare points in 3 different containers. So we have 3 different oddly shaped containers. All of them are filled with the same fluid to exactly the same height. Comparing points A and B should be relatively easy. Point B is at a greater depth than point A, so the pressure at point B must be greater. Comparing points A and E should be relatively easy. They're both at the very top of the fluid. The pressure at point A is essentially whatever the ambient pressure is, usually 1 atm, and the pressure at point E would also be the same pressure, so we can say that P at A and P at E are equal to each other. Comparing points A and F is a little more subtle, but of course we have the same fluid and we can see that F is at a greater depth than A, so we can say the pressure at F is greater than the pressure at A. The pressure at B is equal to the pressure at K. Although points B and K are in different containers, they're both at the same depth and therefore the pressure should be the same. The pressure at point C is also equal to the pressure at point H because once again point C and point H are at the same depth. Notice in all of these cases we're measuring the depth relative to the top of the fluid. In this example, all 3 fluids have the same top point. They have all been filled to exactly the same height. The pressure at point H is equal to the pressure at point L. H is here, L is here. They're both at the same depth relative to the top. Pressure at D is greater than the pressure at M. D is located here at a greater depth compared to point M. And finally, the pressure at H is less than the pressure at N because point H is at a smaller depth compared to point N. Let's end this lecture with a practice problem that requires some calculations. A submarine is stranded on the seabed with its hatch door 20 meters below the surface. The hatch door is circular and 0.45 meters in diameter. Calculate the force that a person must exert to open the hatch door from inside. Air pressure inside the submarine is 0.9 atmospheres. So normally inside a functioning submarine, the pressure ought to be approximately 1 atmosphere. So the sailors inside the submarine are naturally accustomed to a pressure of approximately 1 atm, so we would expect the pressure inside to be 1 atm. This submarine is not a functioning submarine, it's stranded at the bottom of the ocean. So the pressure inside is a very uncomfortable 0.9 atmospheres. To get out, the sailors must open the hatch door. The hatch door is circular, somewhere near the top of the submarine, and it must be pushed outwards to open it. That's going to be difficult because, of course, there's 20 meters of water above head, and the weight of all that water is going to be pushing down on the hatch door, making it quite difficult to push the hatch door outwards. To calculate the required force, let's begin with a simple force diagram. So let's say the hatch door is located here. To get out, the people inside or the person must push outward on the hatch door, so this is the force of the person. Inside the submarine, there's some air. That air has some pressure, and that pressure exerts some force on the hatch door. I'm calling that force the force of the inside fluid. The inside fluid is simply the air inside the submarine. Of course, outside there is another fluid, that's water, and that fluid is exerting a force. I'm calling that force F out. F out is essentially the weight of all the water that's outside the submarine, pushing down on the hatch door, preventing the sailors from opening it. To calculate these forces, we need to know what the pressures are. The pressure on the inside is simply 0.9 atm, but of course you should convert that to pascals. That comes out to approximately 91,000 pascals. To calculate the pressure of the water outside, we use our pressure formula. We assume that the pressure on the surface of the ocean is 1 atm or 101,325 pascals, plus d rho g. D is the depth, which is given to us as 20 meters. Rho is the density of water, which is 1,000 kilograms per cubic meter. You should probably memorize that number. And g, of course, is 9.8. Putting all that into your calculator, you find that the pressure outside of the submarine, due to the surrounding water, is approximately 297,000 pascals. Now we're really interested in forces, and we know that pressure is force divided by area, so let's calculate the area of the hatch door. Area of the circular hatch door is simply pi r squared. Note that 0.45 is the diameter, so divided by 2 to get the radius, and you find the area of the hatch door. Now we can calculate the force of the air inside. F in is going to be pressure inside times the area. Putting all that into your calculator, you will see that the air inside the submarine is helping to open the door. It provides approximately 14,500 newtons of force. Unfortunately, all the water outside is exerting a much larger force. Pressure of the outside water times the area of the hatch door comes out to be about 47,000 newtons. To get out, a person must essentially supply the difference between these two forces. So the force that a person must provide to open the door is going to be F out minus F in, which is approximately equal to 32,784 newtons. That's a relatively large force, incidentally. If you divide it by 9.8, you see that this is the force that's required to essentially lift a mass of 3,345 kilograms. So lifting this kind of a mass is quite difficult, and therefore opening the hatch door of a stranded submarine is nearly impossible unless there is a mechanical device to help you. And that is the end of this lecture. Thank you for your attention.